So in section 7.3, we're going to look at the factors that determine whether a compound is soluble or not, that is, whether it will actually form a solution. And in particular, we're going to focus on what determines whether a substance will form an aqueous solution where the solvent is water. And I'm going to break this into two parts. I'm going to do one video where I look at the factors that affect the solubility of ionic compounds, and then there'll be a second video where I look at the factors that affect the solubility of covalent or molecular compounds. So just to recap, remember that we can recognize that we have an ionic compound because this will be a compound that forms between a metal ion and a non-metal ion. Sometimes though we'll see ionic compounds will form between a polyatomic cation and an anion of some type, which could be polyatomic or monatomic. But it's worth keeping in mind that there is the possibility of a polyatomic cation substituting for the metal ion in an ionic compound. And of course the most common polyatomic cation is the ammonium cation. So what do we mean by solubility? What we mean by solubility is the amount of solute that can dissolve in a given volume of solvent, and we're going to do a whole section on this. But for now, what we're really concerned with are what are the factors that determine how soluble a substance is, whether that be an ionic compound or a molecular compound, in a given solvent. And to begin with, we're going to look at ionic compounds, as I mentioned, and the factors that affect their solubility in water as the solvent. So let's just recap. As we'd explained previously, we said when an ionic compound dissolves in water, the crystalline ionic compound is torn apart by the water molecules into its component ions, and then those individual ions become dispersed throughout the water. So what happens is the water molecules start tugging on the ions that are on the surface of the crystal, and if they can tug sufficiently strong enough to overcome the attractive forces keeping the ion in the crystal, then that ion will move out into the solvent. So what's going to happen is we're going to go from a crystalline ionic compound where all of the ions are tightly bound to one another to a solution where we have the ions dispersed throughout the water, and we've got individual ions with water molecules in between them. Now this is only going to happen if the attractive forces between the water molecules on the ions is greater than the forces between the oppositely charged ions that hold them together in the crystal. So that force ripping the crystal apart has to exceed the force that's holding the crystal together. So what this means is that ionic compounds that have good solubility in water will have weak forces holding the ions into the crystal. So what determines whether the forces between the ions within the crystal? Well, there's two factors that determine the size of that force. The first one is the size of the charges on the ions, and it's a pretty simple relationship here. As the charge of the ions goes up, then the strength of the attraction between the ions will increase. So if I looked at something like an aluminum ion with a 3+ charge interacting with a phosphide ion with a 3- charge, that's going to be a really strong interaction if we compare it with something like a sodium ion interacting with a bromide ion where the charges are a lot smaller. Now, you know how to determine the ionic charges on cations and anions by looking at the position of the atom in the periodic table. So you'll be able to judge the sizes of the ionic charges for a given ionic compound. Now, the other factor that's going to affect the strength of interaction between two ions in a crystal is the radius of the ions. And this is a pretty simple relationship. The smaller the ions, the stronger the relationship, the strength of attraction. So small ions have a really strong attraction, and then bigger ions, it's weaker because the charge is more dispersed. So that's the general rule. Now we will have to think about how does the radius of an ion vary with its position in the periodic table. We already know about how the charges vary with the position in the periodic table, but what about the radius of the ions? And it's a pretty, there's a few sort of general principles here. The first thing to note, though, is that when you look up values of the radius of these ions, you might see that there's slight variation depending upon the source of the information that you look at, just slight variances in the information. And the reason is the way that they determine the radii of an ion is by actually looking at a crystalline ionic compound and then measuring the distance between the center of one ion and the center of the, or that they have to define the boundary between where that ion interacts with a neighboring ion. So what happens is when you have different pairs of ions, say we have a sodium ion with a bromide ion, you actually end up with a slightly different radius when you have different combinations of ions, but it's always going to be around about the same number. So I think in sodium bromide, it turns out that it's a little bit bigger, but it's about the same. So don't get too hooked up on the exact value. We're going to be focusing on general trends for ionic radii. And the first thing to recognize is that cations, which are formed by losing electrons, are smaller than the atoms that they are made from. So a sodium atom has 11 electrons and a sodium ion has 10 electrons. So it's not surprising that a sodium ion is smaller than a sodium atom because the electrons are on the outside of the atom, and if we take one away, we're going to be taking something from the outer edge of the atom that's going to make it smaller, right? Now, anions are going to be larger than the atoms that they are made of. So if we look at something like a chlorine atom has 17 electrons. If we add an electron to it to make a chloride ion, where do we add the electron? To the outer edge of the atom. It makes it bigger, and so for that reason anions are larger than their parent atoms. Now, the final sort of trend that we're going to see is that as we go down a group in the periodic table, then ionic size gets bigger, and that's not surprising because remember, every time we move a row down into the periodic table, we're starting another layer of electrons, so our atoms get bigger and bigger and bigger because moving down one period is equivalent to adding another layer of electrons to our atom. So those are the general rules that we're going to use to judge the size of ions when we're thinking about how strongly ions interact within a crystal. So here we go. We can see some of these trends here. Here's a lithium, and you can see that the lithium cation is a lot smaller than the lithium atom. Here's oxygen, and you can see the oxide anion is a lot bigger than an oxygen atom. So that's our first trend there. Our first 2 points here: cations are smaller than their parent atoms, and then anions are larger than their parent atoms. Now the next point was, as we go down a group, that the ions tend to get bigger, and you can see here as we go from lithium plus to sodium plus to potassium plus, we're adding another layer of electrons. The lithium ion, 2 layers of electrons. Sodium ion is in the third period, 3 layers of electrons, so forth. As we go down, they get bigger and bigger. And it doesn't matter, that trend holds for the anions as well. It doesn't matter whether it's anions or cations. Now, when you go across the periodic table, it's very similar to what we see for atomic size. As you go across, you tend to see a small decrease in the size of the cations and a small decrease in the size of the anions. But it's not a particularly big trend. You can see that there's hardly any difference here as we move across here. But the general trend is, as you move across, they tend to get smaller for a given set of cations or a given set of anions. Now, I talked about the charge as being the other factor alongside the ionic radii that affects the strength of interactions of ions in a crystal, and we can often get the charge of a monatomic ion from the position of the parent atom in the periodic table. Remember, group 1a metals form +1 ions, group 2a metals form +2. Silver always forms a +1, zinc and cadmium always form +2, aluminum and gallium always form +3, and then we go into our non-metals which form anions. Those in the nitrogen group, group 5a, always form -3 anions. Those non-metals in group 6a always form 2- anions, and those non-metals in group 7a, the halogens, they always form 1- anions. Now, the other way you can determine the charge of an ion, of a monatomic ion, is from the formula from the name. So if we have something like iron 3 chloride, well, we know that it must have the Fe3+ ion present because it's described as being iron 3. So that would be a good example of pulling it from the name. Okay, so let's look at an example of how we can put these two rules together. Basically, the weaker the interactions between the ions in the crystal means it's going to be more soluble in water. The things that lead to weak interactions between the ions are going to be a low charge of the ions, and they're going to be big radius of the ions, right? They're going to lead to weak interactions, and those things mean that it's going to be more soluble. So it says here, which would you predict to be more soluble in water, iron 3 chloride or sodium chloride? And then you have to explain your reasoning. Now, you don't have to be correct. You don't have to give the correct answer. You just have to have a logical answer when you're doing these explain your reasoning type problems. So we need our formulas. We've got FeCl3, which is going to be composed of Fe3+ ions and Cl- ions, and we've got sodium chloride, NaCl, which is composed of sodium ions and chloride ions. So the first thing you notice is that they both contain the chloride ion. That's a common ion. So that's not really going to help us thinking about that because they both have that in common. Well, what we need to know is the radius and charge of the sodium ion and the iron 3 ion so that we can start making some decisions. So sodium is in group 1a, so it has a charge of +1, and I just looked in Wikipedia and I found that the ionic radius is about 102 picometers. Depends on the compound that it's in, but it's around that number. Iron, it's iron 3, right? So we know that it is an Fe3+, as the cation has a charge of +3. And again, I just looked in a table of ionic radii online, and depends on the compound, but it's around about 70 to 80 picometers. So what I see here is that Fe3+ has a really high charge and a really small radius. So high charge, small radius, and that means that its crystals are going to be held together really strongly, right? So what that means is that we'd expect that it to have lower solubility in water because it's just harder to pull apart, okay? So I would predict that FeCl3 would have the lowest solubility in water compared to NaCl. So that's an example of how we use these two factors to compare the relative solubility of ionic compounds. Now, it turns out that most of the time what we're going to be doing in Chemistry 161 is looking for whether a compound is soluble or insoluble. And so for ionic compounds, what we'll often do is use these tables of solubility rules. And there's one of these is given in the ALEX program. So what you do is you just take your cation and then you find your anion and you find where they intersect, and it tells you whether it's soluble or not. So let's see. So here we can see that barium hydroxide would be soluble. So barium is a 2+, OH minus, it's 1 minus, so we'd have to do crossover. So this would be BaOH2, and that guy would have good solubility in water because this is a table of solubility rules for aqueous solutions. Now, if I go to something like cadmium, or let's do cadmium carbonate, and we'll go across, and we can see that cadmium carbonate doesn't dissolve in water. So cadmium is 2+, carbonate CO3 2-. They have equal and opposite charges, so they're going to combine 1 to 1. So that guy doesn't dissolve well in water. So that's in reality how we'll frequently determine, just in a binary fashion, either yes soluble, no not soluble, whether an ionic compound is soluble in water. And like I said, you can find lots of tables like this online, and there's one in Alex, there's another one in your textbook. Okay, so that concludes this short video on how we determine the solubility of ionic compounds, and also how we can kind of compare the relative solubility of different ionic compounds on the basis of the charge of the ions involved and also the radii of the ions.